Let the weight of the day slip away for a moment. Whatever you've been carrying, whatever's been pulling at your thoughts, just set it down here beside you. Tonight, we're chasing a beautiful mystery. Why light, the fastest thing in existence, has a speed limit it can never break, and why that limit shapes everything: time, space, the way you see even the atoms in your bones. Where are you right now? Is your room quiet, dim, warm? Are you curled under blankets or watching the night settle in? If this calm finds you, you're welcome to stay. Maybe leave a quiet, like a soft subscribe, or just let the story carry you, no rush, at exactly the speed you need. So close your eyes if you'd like. Get comfortable. And let's begin now. Light is one of those things we all think we understand until we actually try to explain it. You flip a switch, and there it is. It fills the room, lets you see your cat's judgmental stare from across the kitchen, makes your phone screen glow long after you swore you'd put it down for the night. It's everywhere, always arriving exactly when we need it, like a friend who never knocks, but somehow always knows when to show up. But what is it really? Is it a wave? A particle? Some kind of cosmic messenger with a very strict delivery schedule? The short answer is yes, and also sort of, and it depends on how you're looking, which is exactly the kind of answer that makes physics both frustrating and beautiful. Let's take a nice slow wander through what light actually is, because before we can understand why it has a speed limit, we first need to understand what's actually doing the speeding. First, let's talk about photons. These are the tiny packets that make up light. Imagine them as little messengers zooming through the void at the fastest speed allowed by the universe. But these messengers are strange. They're not particles in the traditional sense, not like marbles or grains of sand or the pebble you once kept in your pocket for no particular reason. They don't have mass, they don't rest, and they definitely don't follow the usual rules of things that move through space. Here's where it gets quietly wonderful. Photons are also waves, but not waves like ocean waves or the ones you make when you shake out a bedsheet. They're electromagnetic waves, vibrations of electric and magnetic field that oscillate at right angles to each other and to the direction they're traveling. Yes, it sounds a bit like a physics yoga class, but the mental image is actually quite elegant. Two fields dancing through space together, locked in a perfect rhythm, never touching, but forever intertwined. These waves don't need a medium to travel through. That's important, and it's also deeply strange if you think about it. Most waves sound waves, water waves, even the polite wave you give your neighbor from across the fence, needs something to move through. Sound needs air or water, or something solid to push against. Water waves need well water, but light just goes. It travels through the vacuum of space without a problem, without slowing down, without needing any kind of road or track or material to carry it along. That's why we can see the sun, which is over 90 million miles away. Its light has traveled through the emptiness of space to reach us without a single rest stop, without asking for directions, without complaining once about the journey. And it does this every single day, quietly, reliably, like the most dedicated delivery service in the universe. And light doesn't just come in one flavor. The light we can see, what we call visible light, is only a tiny slice of the electromagnetic spectrum. Imagine a piano that stretches for miles in both directions. Visible light is just a handful of keys somewhere in the middle, the ones we happen to be able to hear. On one end of this cosmic piano, you've got radio waves, long, lazy undulations that can stretch for miles, carrying your favorite songs and talk shows through the air. On the other end, you've got gamma rays, sharp and energetic spikes that can pass through almost anything and are usually found in the company of exploding stars and nuclear reactions. In between, you've got microwaves, which heat your leftovers, infrared, which your TV remote uses to talk to your television, ultraviolet, which gives you sunburns if you're not careful, and X-rays, which can see through your skin and bones, but somehow never manage to find your missing socks. But despite all these differences, despite the fact that radio waves are lazy and gamma rays are intense and visible, light is somewhere comfortably in the middle. All these forms of light move at the same speed in a vacuum, roughly 299, 792, 458 meters per second. That's just under 300,000 kilometers every single second. A number so big, it feels almost like nonsense, like the universe is playing a joke on us. It's like asking, "How fast is that?" And the universe just shrugs and replies, "Yes." To put it in more bedtime-friendly terms, if light were a runner, it could jog around the entire Earth more than 7 times in a single second. Not bad for something with no legs, no shoes, and no need to stop for water breaks. But here's something else to tuck away in your mind. As you drift, light doesn't always go that fast. In a vacuum, sure, it's got a clear track and no traffic. But when it passes through something, water glass, even a diamond, it slows down. Not because it's tired or lazy, but because it's interacting with the atoms in the material. It's a bit like walking through a crowded room at a party. You're still heading toward the snack table, but there's a lot more bumping into people, a lot more "excuse me" and weaving around conversations. That slowing down is what causes refraction, the bending of light when it moves from one material into another. That's why a straw looks bent when you put it in a glass of water. That's why diamonds sparkle so brilliantly. The light inside them is constantly being delayed, rerouted, bouncing around, like it's lost in a beautiful, crystalline maze. It's all about how light's journey gets interrupted, bent, and scattered by the materials it passes through. But here's the twist. The thing that makes this even more quietly miraculous, even though light slows down in these materials, individual photons still travel at the same speed between atomic interactions. They're just taking a more complicated path, bouncing and zigzagging, like someone trying to speed walk through a dance floor full of enthusiastic uncles at a wedding. Now, let's talk for a moment about color. When we look at a rainbow or light passing through a prism, or that weird oily shimmer you sometimes see in a puddle, what we're actually seeing is light split into its various wavelengths. Each color of visible light has a different wavelength. Red is long and lazy, like a slow rolling wave. Violet is short and twitchy, vibrating much faster. But all of them, red, orange, yellow, green, blue, violet, are still photons, still electromagnetic waves, just vibrating at different frequencies. Your eyes have special cells called cones, and they're tuned to specific ranges of those wavelengths. That's how you see color. It's not that the apple sitting on your counter is red in some absolute sense. It's that the apple is reflecting the wavelength we interpret as red while absorbing all the others. In a way, color is just your brain's best guess, its translation of which vibrations made it through space and into your retinas. And here's the part that might just lull you into a peaceful sleep. Light also has no rest mass. That means, unlike you, or me, or your slightly judgmental cat, photons don't need energy to keep moving. They always move. They have no choice. If a photon were to stop, it wouldn't just be taking a break. It would cease to exist. Motion or nothing. All or gone. That's not just poetic, it's physics. So let's gather what we know so far before we drift any further. We've got these massless packets of energy that behave like both waves and particles. They travel at a universal speed. They can interact with atoms, bend around corners, bounce off surfaces, pass through some things and get absorbed by others. And all the while, they're delivering the very experience of sight and color to conscious brains like ours, painting the world in shades and hues, letting us see faces and stars and pages of books. And that's just scratching the surface. But for tonight, let's hold on to this image light as a restless traveler made of no substance but energy, never pausing, never sleeping, always tracing the outlines of everything we know. It shows us the stars, the faces we love, the glow of a candle on a quiet evening. And it does all of this while obeying one of the most curious rules in the universe, a speed it will never exceed and never fall below. Light isn't just what helps us see. It's how the universe whispers its story into our eyes. And now that we've met this strange and beautiful traveler, let's ask what happens when light tries to move through things that aren't empty space. We've just spent some time getting to know light in its purest form, zipping through the vacuum of space at 300,000 kilometers per second, unbothered, untethered, unstoppable. But the universe isn't just empty space. It's full of things. Water and glass and air and skin and diamond and dust. And when light encounters these things, something quietly fascinating happens. It slows down. Not because its tired photons don't get tired. Not because it's changed its mind about where it's going. But because it's bumping into atoms interacting with matter in ways that add little delays to its journey. And those delays, those small interruptions, are what make the world around us shimmer and refract and sparkle. Let's imagine light traveling through a vacuum. It's got a clear road ahead, no obstacles, no traffic. It moves in a straight line, at its maximum speed, the cosmic speed limit, no questions asked. But now, imagine that same beam of light entering a glass of water. Suddenly, the road isn't so clear anymore. There are atoms everywhere, oxygen, hydrogen, all jostling and vibrating. The light has to navigate through this crowd. It's a bit like trying to walk through a busy train station at rush hour. You're still moving forward, still heading toward your destination, but you're constantly weaving, adjusting, saying "excuse me" under your breath as you slip between people. That's what light does when it enters a material. It interacts with the electrons in the atoms, gets briefly absorbed and re-emitted, and in all that back and forth, it effectively slows down. This is why light moves slower in water than in air, slower still in glass, and slowest of all in diamond, where the atoms are packed so tightly that light has to take the scenic route through a maze of interactions. But here's the beautiful part. Even though the light as a whole appears to slow down, each individual photon is still moving at the speed of light between interactions. It's not that the photons themselves get sluggish, it's that the path becomes longer, more complicated, like someone trying to sprint through a dance floor packed with enthusiastic uncles doing the Macarena at a wedding. The photon is still moving at full speed, it's just doing a lot more zigzagging. This slowing down, this interaction between light and matter, is what gives rise to one of the most enchanting phenomena in physics refraction. That's the bending of light when it passes from one material into another. You've seen it 1,000 times. A straw in a glass of water looks bent or broken at the surface. Your legs look shorter when you're standing in a swimming pool. A spoon in a teacup seems to shift and warp. It's all because light changes speed when it moves between air and water, and that change in speed causes the light to bend, to shift direction slightly. The light isn't being dishonest. It's just obeying the rules, adjusting its path according to the material it's traveling through. And this isn't just a quirky party trick. Refraction is the principle behind eyeglasses, which bend light just enough to help you see clearly. It's behind microscopes, which let us peer into worlds too small for the naked eye. It's behind telescopes, which gather distant starlight and focus it so we can see galaxies billions of light years away. It's behind cameras and projectors and every lens that's ever helped us see better, closer, clearer. And then there's the sparkle of a diamond. Why do diamonds glitter so beautifully? Because light entering a diamond slows down significantly. It bends sharply as it enters, bounces around inside, gets reflected multiple times off the internal surfaces, and eventually exits at odd angles, split into all its component colors. What you see is light taking the long way out, turning a simple beam into a cascade of tiny rainbows. The diamond isn't creating light. It's just giving light a complicated, beautiful journey. This interplay between light and matter also explains something you might have wondered about. Why does a prism split white light into a rainbow? It's because different wavelengths of light, different colors, slow down by slightly different amounts when they enter the glass. Red light, with its long lazy wavelength, bends the least. Violet light, short and energetic, bends the most. So when white light, which is really all the colors mixed together, enters a prism, it gets spread out, separated into its individual hues, like a choir breaking into solo voices. Each color is still light. Each one is still made of photons. They're just vibrating at different frequencies, and the material they're passing through treats them slightly differently. Now let's talk about color itself, because it's easy to forget how strange and wonderful it really is. When you look at a ripe strawberry and see red, what's actually happening? The strawberry isn't glowing. It's not generating red light. It's absorbing most of the light that hits it and reflecting back only the wavelengths we interpret as red. Your brain receives that reflected light and says, ah, red. But in another sense, the strawberry is every color except red because it's absorbing all those other wavelengths and only rejecting a red. Color, in other words, is a conversation between light matter and your mind. The object reflects certain wavelengths. Your eyes catch them. Your brain interprets them. And somewhere in that process, the world becomes painted in meaning warm reds, cool blues, soft greens, the golden glow of late afternoon. It's not that color doesn't exist. It's that color is relational, contextual, a product of how light dances with the surfaces it touches, and how our biology translates those dances into experience. And all of this, the bending, the slowing, the splitting, the reflecting happens because light, for all its speed, is also deeply interactive. It doesn't just pass through the world untouched. It touches back, it responds, it adapts. But even in all this bending and slowing, there's something unwavering underneath. Those photons zigzagging through glass or water or your cornea are still obeying the same fundamental rules. They're still moving at light speed between each interaction. The universe hasn't changed the speed limit. It's just made the road a little more winding. So the next time you see a rainbow after a rainstorm, or notice how a glass of water makes everything behind it look just slightly off, take a quiet moment to appreciate what's really happening. You're watching light slow down, bend, split, and reveal its hidden colors. You're seeing the universe's speed limit getting tested, softened, complicated by matter. And somehow, in all that complication, the world becomes more beautiful. But if light can slow down when it meets matter, how did we ever figure out how fast it goes in the first place? That's a story full of lanterns, moons spinning wheels, and stubborn curiosity. Let's take a gentle step back in time. Long before satellites and lasers, before physicists had high-tech instruments to measure the secrets of the universe. Imagine a world lit only by fire and stars, where understanding something as elusive as the speed of light wasn't just difficult, it seemed almost absurd. For most of human history, people believed that light moved instantaneously. It was just there. You lit a candle, and the room filled with glow. The sun rose, and the world turned golden. No delay, no waiting, no journey. It felt obvious. Why would anyone think otherwise? Even Empedocles, an ancient Greek philosopher, and one of the few who dared suggest that light might travel at a finite speed, wasn't taken very seriously. Aristotle, whose opinions had the unfortunate habit of sticking around for centuries, like an old song you can't get out of your head, thought light was instantaneous. And that, for a very long time, was that. Case closed. Curiosity shelved. But then came Galileo. Now, Galileo Galilei was not the kind of person to accept something just because someone important once said it. He liked to poke at things, drop them off towers, point telescopes at moons, and ask inconvenient questions. And around the year 1638, he decided to try something wonderfully, charmingly optimistic. He wanted to measure the speed of light. The idea was simple, or at least it seemed simple. Galileo and an assistant would each take a lantern and stand on hilltops about a mile apart. Galileo would uncover his lantern first. As soon as his assistant saw the flash, he would uncover his own lantern in return. Galileo would then measure the time between sending his signal and seeing the response. Now, even under the best circumstances, this experiment was, let's say, ambitious. Human reaction time alone is about 1/4 of a second. Light, meanwhile, takes less than a 10,000th of a second to travel a mile. It's a bit like trying to measure the speed of a bullet with a sundial. The tools just weren't up to the task. Still, you have to admire the effort. Picture it, two men on darkened hills waving lanterns at each other, trying to catch something moving faster than thought itself. Galileo unsurprisingly concluded that if light did have a finite speed, it was far, far too fast for him to measure with lanterns and hills and human reflexes. Which was true, but at least the question had been asked. At least someone had wondered. Fast forward a few decades to 1676, a Danish astronomer named Ole Romer was doing something that had nothing to do with measuring light speed. He was watching the moons of Jupiter, particularly a moon called Io, which orbits the giant planet like a tiny reliable clock. By carefully observing when Io disappeared behind Jupiter and when it reappeared on the other side, astronomers could predict its schedule with impressive accuracy. But Romer noticed something odd. Sometimes Io appeared a little late. Other times it seemed to arrive a bit early. At first glance, this might look like sloppy timekeeping, like Io was running behind schedule or showing up too eager. But Romer had a brilliant, quiet thought. What if it wasn't Io being inconsistent? What if it was us? What if the delay was caused by the fact that Earth in its own orbit around the Sun was sometimes farther from Jupiter than at other times? And if that were true, then the light carrying the image of Io had farther to travel when Earth was on the opposite side of its orbit, which would mean light takes time to travel. And just like that, the idea of light having immeasurable, finite speed began to take real shape. From the timing discrepancies in Io's appearances, Romer estimated that it took light about 22 minutes to cross the diameter of Earth's orbit, a distance we now know to be about 186 million miles. His estimate wasn't perfect. The exact distances weren't well known at the time, and his clocks weren't as precise as ours. But it was revolutionary. It told the world light isn't instant. It travels. It has a speed, and we can measure it. For the first time, humanity had caught a glimpse of light in motion. The next leap came in the early 1800s, when a French physicist named Hippolyte Fizeau decided to bring the experiment back down to Earth. His method involved a beam of light, a rapidly rotating toothed wheel, and a mirror placed several kilometers away. Here's how it worked. The light beam would pass through a gap between the teeth of the spinning wheel, travel to the distant mirror, and bounce back. If the wheel was spinning slowly, the returning light would pass back through the same gap and be visible. But if the wheel spun fast enough, by the time the light returned, a tooth would have rotated into place and block it. By carefully adjusting the speed of the wheel, Fizeau could figure out exactly how fast it needed to spin for the light to be blocked. And from that, using the known distance to the mirror and the speed of the wheel, he could calculate how fast the light was moving. His result, about 313,000 kilometers per second. Not perfect, but impressively close to the real value, especially considering he was working with Geer's mirrors and a lot of patience. Not long after, another scientist, Léon Foucault, refined the technique using rotating mirrors instead of toothed wheels, improving the precision even further. And in doing so, he discovered something important. Light moves slower in water than it does in air. This was a critical clue that light interacts with materials in ways that affect its speed that it's not some untouchable, ethereal thing, but something that responds to the world it moves through. But perhaps the most iconic name in this story is Albert Michelson. In the late 1800s, Michelson took Foucault's rotating mirror method and fine-tuned it to a level of precision no one had achieved before. He used long tunnels, carefully aligned mirrors, and incredibly precise timing instruments. His results stunned the scientific world and earned him the Nobel Prize in Physics in 1907, making him the first American to receive that honor. Not a bad reward for chasing beams of light around with mirrors. Today, of course, we have even better tools: lasers, atomic clocks, satellites that can measure distances to within a hair's width. We've become so precise that in 1983, scientists did something remarkable. They stopped measuring the speed of light altogether. Instead, they defined the meter based on the speed of light. Since 1983, 1 meter has been officially described as the distance light travels in exactly 12999,792/458 of a second. In other words, we flipped the equation. We no longer ask, how fast does light go? We say light goes this fast, and we'll measure everything else against it. The speed of light has become the ruler by which we measure the universe. But it all started with curious minds, imperfect tools, and a stubborn refusal to believe that something so fundamental could remain forever out of reach. From Galileo on his hilltop, to Roemer watching Jupiter's moons, to Fizeau spinning his wheel, each step brought us closer to understanding one of the universe's most essential truths. The speed of light isn't just a number, it's a story of human curiosity, refusing to accept we can't know as an answer. And now, with that number in hand, carefully measured and universally agreed upon, we can finally ask the question that truly matters. Why that number? Why does light move at exactly that speed, and not faster, not slower, not infinitely fast? The answer, it turns out, was hiding in the equations of a brilliant mind who saw connections no one else had noticed. So now we know what light is: a strange hybrid of wave and particle traveling through space at a fixed speed. And we know how we measured that speed: through centuries of clever experiments, stubborn curiosity, and increasingly precise instruments. But knowing the speed and understanding why it has that particular value are two very different things. Why doesn't light just go faster? After all, it seems like such an arbitrary number. Why 299,792,458 meters per second? Why not a nice round 300 million? Why not 500 million? Why not just infinite? What's stopping this massless, ethereal bundle of energy from moving as fast as it wants? Why does the universe insist on giving it a speed limit at all? To understand this, we need to take a calming stroll into one of the most elegant and mind-bending parts of physics electromagnetism. More specifically, we need to talk about a man named James Clerk Maxwell. In the 1860s, Maxwell did something extraordinary. He took everything scientists knew about electricity and magnetism, at the time think Benjamin Franklin's experiments with lightning, Michael Faraday's work with magnets and coils, and he wove it all together into 4 beautiful mathematical equations. These are known somewhat unimaginatively as Maxwell's equations. They describe how electric fields and magnetic fields interact, how they change over time, and how they move through space. Now, you don't need to worry about the equations themselves. No one's going to quiz you at bedtime. But here's the part that should make you sit up a little. Even as you're drifting, when Maxwell combined these equations, he discovered something completely unexpected. They predicted the existence of waves. Not sound waves or water waves, but electromagnetic waves, ripples made of oscillating electric and magnetic fields, each one generating the other as they travel through space. And these waves, according to the math, would naturally move at a very specific speed. Maxwell plugged in the known values for the electric and magnetic constants of empty space, did the calculation, and out came a number. That number was 299,792,458 meters per second. Maxwell stared at this result and realized something profound. That number, the speed his equations predicted for electromagnetic waves, matched the best measurements scientists had for the speed of light. This wasn't a coincidence. This was a revelation. Light, Maxwell understood, was an electromagnetic wave. It was a self-propagating ripple of electric and magnetic energy traveling through the void at a speed dictated not by chance, not by preference, but by the very structure of the universe itself. Let that settle in for a moment. The speed of light isn't just a quirk or a habit. It's built into the equations that govern the fabric of reality. It's not like the universe randomly spun a dial and happened to land on that particular number. It's more fundamental than that. If electric fields and magnetic fields exist, and they definitely do, then electromagnetic waves must travel at this speed. There's no other option. The math doesn't allow for anything else. So, that's part of the answer. Light moves at the speed it does, because that's the only speed electromagnetic waves can travel in a vacuum. Anything faster or slower would break the laws of physics as we understand them. The speed of light is written into the universe's instruction manual in a chapter that can't be edited or revised. But now let's go one step deeper, because knowing that light must go this speed still doesn't answer the bigger question: why can't anything go faster than that? After all, in everyday life, we're used to speed being somewhat negotiable. If your car goes 100 kilometers per hour, you can push it to 110 if you're feeling bold. But with light, there's no upgrade option, no turbo mode, no way to coax it into going just a little bit faster. Why, to answer that, we need to call in someone you've almost certainly heard of: Albert Einstein. In 1905, Einstein published a paper that would change everything. It was called "On the Electrodynamics of Moving Bodies," though today we know it simply as the special theory of relativity. And buried within that paper was a statement so bold, so counterintuitive, that it redefined our understanding of space-time and motion. Einstein's key insight was this: the speed of light in a vacuum is the same for all observers, no matter how fast they're moving. Read that again slowly. It sounds almost too simple to be revolutionary, but it is absolutely beautifully bananas. Imagine you're on a spaceship gliding through space at 90% the speed of light. Very impractical for a commute, but excellent for thought experiments. You turn on a flashlight and point it forward. Common sense would tell you that, from the perspective of someone standing still, the light from your flashlight should be moving faster. After all, it's got your speed, plus its own speed, right? But no, both you on your speeding spaceship and the person floating, still in space, would measure the speed of that light beam as exactly the same 299,792,458 meters per second. Not a bit more, not a flicker less, exactly the same. This breaks everything we think we know about how speeds add up. If you're walking forward on a moving train, your speed relative to the ground is your walking speed, plus the train's speed. That's obvious. That's intuitive. But light doesn't play by those rules. Light says, I don't care how fast you're moving. I'm always going to move at the same speed relative to you. To make that possible, to preserve this cosmic speed limit, reality itself has to bend. Time slows down for you as you go faster. Distances contract in the direction you're moving. Your mass increases, requiring more and more energy to accelerate you further. The universe warps space and time around the speed of light to ensure that no one, no matter how fast they're going, can ever measure light moving any faster or slower than that fixed universal constant. And here's where things get truly mind-bending. If you tried to accelerate yourself to the speed of light, you'd run into an impossible problem. As you get faster and faster, your mass not in the "I ate too many cookies" sense, but in the "you now require more energy to accelerate" sense trends toward infinity. And to actually reach the speed of light, you'd need infinite energy. Infinite energy is a pretty tall order, even for the most ambitious travelers. So no matter how hard you try, no matter how powerful your engine, you can get close to the speed of light, but you can never quite reach it. You can chase it, but you'll never catch it. It's always just out of reach, like trying to grab your own shadow. And that's why the speed of light isn't just the speed of light. It's the cosmic speed limit, the upper boundary on how fast information, energy, or anything with mass can travel through the universe. It's a barrier woven into the structure of space-time itself, a rule that even the most determined physicists can't break. Here's a thought to ease you towards sleep. If the speed of light weren't limited, everything would fall apart. Causality, the idea that causes happen before effects would break down. You could, in theory, see an effect before its cause. You could send messages backward in time. Paradoxes would pile up. Time travel would create logical nightmares. Instead, the universe protects us from that kind of chaos with this elegant speed limit. It keeps things ordered, predictable, calm. No matter what else changes, the speed of light stays the same. It anchors reality. It gives time a direction and events a sequence. So, the next time you watch a sunset, or marvel at the stars overhead, or notice the way light filters through your window in the late afternoon, remember those beams of light didn't just happen to arrive. They followed a rule written into the very bones of physics, a rule that says this far, no farther, a limit, yes, but a limit that gives the universe structure, stability, and beauty. Light doesn't go faster because it can't, not because it's weak, not because it's lazy, but because it's perfect, exactly as it is, bound to a speed that keeps time flowing forward, keeps causality intact, and allows us to understand the world in a way that would otherwise be impossible. And honestly, for something that zips across space at nearly 300,000 kilometers per second, that's a pretty graceful pace. But understanding the limit is one thing. Seeing what happens when that limit shapes reality, when it bends time, warps space, and rewrites the rules of existence, that's where things get truly strange. Albert Einstein had a gift for taking the universe's whispered secrets and turning them into statements so clear, so inevitable, that afterward they seemed obvious, like the universe had been trying to tell us all along, and Einstein was just the first person who actually listened. When he introduced his theory of special relativity in 1905, he didn't just tweak the rules of physics, he rewrote them. And at the heart of his theory was that bold, unshakable statement we just explored: the speed of light in a vacuum is constant. Not mostly constant, not pretty consistent if you're not moving too fast, absolutely unchangeably constant for everyone, everywhere, always. This sounds simple enough when you're half asleep and letting your thoughts drift, but it shatters everything you think you know about motion and time. Let's walk through it gently, the way Einstein himself might have sitting beside you with a cup of tea on a quiet evening. Imagine you're on a spaceship floating peacefully through the void of space. You're holding a flashlight. You turn it on, and a beam of light shoots out in front of you at, say it with me, 299,792,458 meters per second. Now imagine someone else, let's call them your co-pilot, flying past you in another spaceship, traveling at half the speed of light. From their perspective, you and your spaceship are whizzing by in a blur. But when they measure the speed of that same beam of light coming from your flashlight, they don't see it moving any faster or slower. They also measure it at exactly 299,792,458 meters per second. That's weird. Like deeply, fundamentally weird. In the everyday world, speeds add up. If you're walking forward on a moving train, your speed relative to someone standing on the platform is your walking speed plus the train's speed. That's intuitive. That's how motion works in our daily experience. But with light, the rules change. The train could be moving, you could be moving, the flashlight could be moving, and the speed of light stays exactly the same for everyone measuring it. So, what gives Einstein's solution was as beautiful as it was unsettling. It's not the speed of light that changes, it's everything else. Time, space, the passage of moments, the size of things, all of it bends and stretches to preserve that one sacred number. Let's gently walk through the consequences. First-time dilation. This one is a favorite among physics students and science fiction writers alike. And for good reason, it's both mathematically precise and utterly mind-bending. The faster you move through space, the slower time passes for you compared to someone who's standing still. Not subjectively, not metaphorically, actually. Let's say you're on a spaceship traveling at 90% the speed of light. To you, everything on board feels perfectly normal. You eat snacks, you read a book, you wonder why you didn't pack more socks. Time ticks along at what feels like its usual pace. But when you return to Earth after what feels like a short trip, you might discover that much more time has passed for everyone else. Years, even decades. While you experienced a brief journey, Earth aged without you. This isn't science fiction. This is science fact. We've tested it with atomic clocks flown on airplanes. We've observed it in particles created by cosmic rays high in the atmosphere. Particles called muons, which normally decay in just a few microseconds, last much longer when they're traveling near the speed of light. Their internal clocks slow down. Time literally stretches for them as they move, allowing them to survive long enough to reach the ground and be detected. Time actually physically slows down when you move fast. The universe isn't playing tricks. It's rewriting the schedule. Next length contraction. This is time dilation's strange twin. When you travel at high speeds, objects in the direction of your motion appear shorter, not because of some optical illusion, but because they physically are shorter from your perspective. Your spaceship would literally measure shorter along its path of travel to an outside observer. Now, before you start imagining yourself squishing into an uncomfortable pancake, this effect only becomes noticeable at speeds close to the speed of light. For everyday travel cars, planes, even very enthusiastic joggers, the effect is so minuscule, it might as well not exist. But near light speed, the universe gets squishy. Space compresses. Distances shrink. The faster you go, the shorter the road becomes. And then there's the relativity of simultaneity, which sounds like a tongue twister, but is actually a lovely bit of mental yoga. It means that two events that seem to happen at the exact same time for one person might not happen at the same time for someone else if they're moving relative to each other. Imagine a train moving very fast. In the middle of the train, a light bulb flashes. From the train passenger's point of view, the light reaches the front and back of the train at the same moment. After all, the light travels the same distance in both directions at the same speed. But from the perspective of someone standing on the platform, watching the train zoom past, the light reaches the back of the train first, because the back of the train is moving toward the flash, while the front is moving away from it. Both observations are correct. Time and space are no longer universal, unchanging backdrops. They're flexible, they're local, they're relative. All of this strangeness, time stretching distances, shrinking simultaneity, breaking down happens to protect that constant speed of light. It's as if the universe looked at this one number and said, everything else can bend, but this must not break. It's a delicate balancing act, a cosmic contract. In exchange for allowing light to remain constant, the universe agrees to warp everything else around it. And here's a soothing thought to carry with you into sleep. This cosmic speed limit is what protects our sense of before and after, because light can only travel so fast, information can only travel so fast. That means you can't see an event before it happens. You can't send a message into the past. The speed of light keeps the universe logical, predictable, tidy. Without it, things would get messy. You could, in theory, cause effects before their causes. You could receive a reply before you sent the message. Paradoxes would stack up like dishes in a sink no one's bothered to clean. Instead, the universe gently says, no, let's not do that. Let's have order. Let's have a maximum speed, and let's make it sacred. And so, this is where Einstein's work shines brightest. He didn't just describe the speed of light as a limit. He showed that it's a cornerstone of reality, the cosmic scaffolding that holds up time and space. Today, GPS satellites rely on Einstein's equations to function correctly, without accounting for both time dilation and gravitational time differences. Your phone would think you're in the middle of the ocean when you're really just looking for the nearest bakery. Particle accelerators use relativity to guide subatomic particles around enormous rings at mind-boggling speeds. Astronomers use it to decode the whispers of distant galaxies, light that's been traveling for billions of years. All of it rests on this strange but constant truth. Light has a maximum speed, and that speed is the same for everyone. So the next time you see a sunbeam falling through your window or a lighthouse flickering in the dark, take a moment to marvel at what that light represents. Not just energy, not just warmth, but the delicate geometry of space-time itself. A quiet contract written in the language of light. And no matter how fast you go, no matter how far you drift, it will always greet you at the same pace, unchanged, unwavering, and eternally on time. We've spent the first part of our journey understanding light itself, what it is, how we measured it, and why it can't go any faster. But knowing there's a speed limit is one thing. Seeing what that limit does to the fabric of reality, that's where things get quietly, beautifully strange. So let's step across that threshold now, from understanding the rule to witnessing its consequences. Einstein showed us that the speed of light is constant, unchanging, the same for everyone, no matter how fast they're moving. And from that one simple statement, the entire structure of space and time had to be rewritten. But there's another consequence of this cosmic speed limit one that's perhaps even more profound, though it whispers rather than shouts. It's this: the speed of light doesn't just limit how fast things can move, it limits what can influence what. It draws boundaries around cause and effect. It tells the universe, you may only connect these dots if there's time for light to travel between them. This idea is what physicists call the light cone. And no, it's not a snack, and it's not a lampshade. It's a way of mapping out which parts of space-time are connected by cause and effect, and which parts are forever separated, unable to touch each other, no matter how much they might want to. Let's imagine this gently, the way you might imagine ripples spreading across a still pond. Picture yourself standing in an open field under a wide sky. You strike a match. That tiny spark sends light out in every direction, forward, backward, up, down, spreading like a sphere that grows larger with every passing moment. The edge of that expanding sphere marks the boundary of what can be influenced by your match right now. If someone is standing far away, say 100 light years away, they won't even know you lit the match until 100 years from now, because that's how long it takes for the light from your match to reach them. Until that light arrives, as far as they're concerned, the match was never lit. The event doesn't exist for them yet. Now flip it around. Imagine you're standing in that same field, waiting for something to happen. The only events that could possibly influence you right now are the ones whose light has had time to reach you. Everything else is too far away in both space and time. That's your past light cone, the collection of all events that could have caused your present moment. The light cone isn't just a clever diagram that physicists draw on whiteboards. It's the border between possible and impossible. If something happens outside your light cone, it's not just too far away. It's too far away in time. No signal, no sound, no whisper from that event can reach you yet. It's as if it doesn't exist for you, not until the light arrives and brings the news. This shapes our entire understanding of the universe. It means there's no such thing as instant communication across vast distances, no perfect synchrony across space, no omnipresent now that everyone agrees on. Instead, every moment is local. Every now is slightly different depending on where you are, and how fast you're moving. And the speed of light is the rulebook that keeps it all consistent. Think about how this affects your view of the night sky. When you look up at the stars on a clear evening, you're not seeing them as they are right now. You're seeing them as they were. The light from the nearest star system, Alpha Centauri, takes more than 4 years to reach us. If something dramatic happened there last week, a flare, an explosion, a cosmic event we won't know for several more years. And that's the nearby neighborhood. Look farther out, and the effect becomes even more striking. The light from the Andromeda galaxy takes over 2 million years to arrive. You're seeing it as it looked when early humans were just beginning to figure out tools and fire. You're looking at ancient light, a postcard from the deep past arriving tonight to paint a soft smudge across your sky. Beyond that, we see light that left distant galaxies billions of years ago, long before our sun even existed. And yet, it feels so present. The stars twinkle, the galaxies glow, they seem right there. But they're not. They're history, written in beams of light, traveling at their own patient, unhurried pace. This delay is what allows astronomers to be time travelers of a sort. When they point their telescopes into deep space, they're not just looking far, they're looking back. Every image captured is a snapshot of the past. The deeper they look, the older the light, the more ancient the story. And all of this insight is possible because light doesn't move instantly. Its speed limit gives us access to history. There's also something deeply elegant about how this delay enforces causality. You can't influence something unless there's time for a signal to get there. That's not just a suggestion, it's a safeguard. It prevents paradoxes. It's the universe's way of saying, let's keep things logical. If you could send signals faster than light, you could, in theory, send a message to your own past. You could warn yourself not to eat that suspicious burrito. And if you listened, you'd never have a reason to send the warning in the first place. That's the kind of logical loop that keeps physicists awake at night, and not in a productive way. But with the speed of light as a firm, unyielding cap, those loops never form. You can't outrun your own consequences. Events happen in order. The past stays behind you. The future lies ahead. It's not just the flow of time, it's the structure of time, and it's protected by this simple, beautiful limit. Now let's bring this down to something more immediate, something you interact with every day. Consider communication. When you make a phone call or send a text, you might not think about the speed of light. But if you're talking to someone on the other side of the planet, there's a very slight delay, tiny but measurable. The signal traveling as electromagnetic waves through cables or bouncing off satellites moves at or near the speed of light. But Earth is big and light, while fast still takes time to cross it. Now think about spacecraft. When mission control on Earth sends a command to a rover on Mars, it can take anywhere from 4 to 20 minutes for the message to arrive, depending on where the two planets are in their orbits. That means if the rover encounters a problem, if it stumbles, if something breaks, the scientists on Earth won't know until nearly half an hour later. There's no real-time remote control. The rover has to be autonomous, making decisions on its own because the speed of light says you're on your own out there. Even your favorite streaming service obeys this limit. Every pixel, every frame of video you watch had to travel from a server somewhere, moving through cables and switches, all at speeds governed by light. It might feel instant, but it's not. It's just very, very fast. It might sound like a constraint, this speed limit on information, but really it's a kind of harmony. The speed of light gives us a universe where effects follow causes, where the past is fixed and the future is waiting. It turns what could be an endless, featureless void into a tapestry of ordered events, each one connected to the next by threads of light that can only travel so fast. And while it might seem strange to think that the fastest thing in the universe is also the thing that slows down how quickly we can know something happened, that delay, those tiny moments of waiting, are what make the universe understandable. They give us distance, perspective, a little room to think, and maybe a little space to rest. The light cone isn't a prison, it's a map that shows us what's reachable, what's knowable, and what still lies beyond the horizon of possibility. It reminds us that the universe, for all its vastness, has structure, and at the heart of that structure is light traveling at its steady, unchanging pace, connecting moments and places and people across the cosmos, one photon at a time. But the light cone is just the beginning. If the speed of light creates boundaries in space-time, what does that mean for how we experience the universe? What happens when we look up at the night sky and realize we're not just seeing space, we're seeing time itself? There's something quietly magical about looking up at the stars on a clear night, the way they scatter across the darkness like salt spilled on a black velvet, the way they seem so still, so timeless, so present. It feels like you're seeing the universe as it is right now, all at once. But you're not. Every photon that touches your eye tonight has been traveling for years, sometimes millions or even billions of years, carrying an image of something that happened long ago. The stars you're seeing aren't where they appear to be. Some of them might not even exist anymore. What you're looking at isn't the universe as it is. It's the universe as it was frozen in light and delivered to you across vast stretches of space and time. Let's start close to home. Relatively speaking, the nearest star system to us, Alpha Centauri, is a little over 4 light years away. That means the light you see from it tonight left that star more than 4 years ago. If something dramatic happened there last Tuesday, a solar flare, an unexpected dimming, anything, you won't see it for another 4 years. For all you know right now, Alpha Centauri could have changed completely, and you'd have no way of knowing until the light carrying that news finally arrives. And that's our neighbor. That's the star right next door, cosmically speaking. Look a bit farther, and the delays get longer. Sirius, the brightest star in our night sky, is about 8.6 light years away. The light you see from it tonight left Sirius in 2016. Betelgeuse, that reddish star in the shoulder of Orion, is roughly 700 light years away. The light arriving at your eyes right now left that star around the year 1325, when the Renaissance was just beginning to stir in Europe, when castles still dotted the countryside and knights rode horses into battle. You're not just looking at distant places, you're looking at distant times. Now let's go farther still, much farther. The Andromeda Galaxy, that soft, hazy smudge you can see with the naked eye on a dark night, if you know where to look, is about 2.5 million light years away. The light from Andromeda that reaches your eyes tonight has been traveling since long before humans existed in any form we'd recognize. It left that galaxy when our ancestors were small ape-like creatures, just beginning to walk upright, just starting to use simple stone tools. Think about that. You're seeing Andromeda not as it is, but as it was, when our entire species was still a distant evolutionary possibility. The photons that touched your retina tonight have crossed unimaginable distances, moving through the emptiness of intergalactic space for millions of years, just to arrive at this exact moment, in this exact place, and gently land on your eye. You are in a very real sense a time traveler, not because you've moved through time, but because time has moved through light to reach you. And the deeper we look, the farther back we see. The Hubble Space Telescope and other powerful instruments have captured images of galaxies so distant that their light has been traveling for over 13 billion years. These are galaxies that formed when the universe itself was young, when stars were just beginning to coalesce out of clouds of hydrogen and helium, when everything was hotter, denser, closer together. We're seeing them as they were in the ancient past, long before our sun existed, long before Earth formed, long before anything in our corner of the universe had even begun to take shape. Every telescope is a time machine. Every photograph from deep space is a fossil, not of bone and rock, but of light itself, light that has traveled across eons to bring us a message from the distant past. This is one of the profound gifts of the speed of light being finite. If light traveled infinitely fast, we'd only ever see the present. We'd have no window into history, no way to watch the universe evolve, no way to see stars being born, galaxies colliding, or the faint afterglow of the Big Bang itself still washing over us in every direction. But because light has a speed limit, because it takes time to travel, we get to look back. We get to see the story of the cosmos unfold in layers, each one older than the last, each one a chapter written in photons and preserved in the patient, steady pace of light. There's a particular kind of light that deserves special mention here, a kind of light so old and so faint that it's almost a whisper. It's called the cosmic microwave background, or CMB. This is the oldest light in the universe, the afterglow of the Big Bang itself, and it's been traveling for nearly 14 billion years, about 380,000 years after the universe began. It cooled enough for atoms to form and for light to finally travel freely without constantly bumping into electrons. That moment, when the universe became transparent, released a flood of light in every direction. And that light is still here, all around us, filling the universe like a soft, invisible glow. It's been stretched and cooled by the expansion of space, shifted down from visible light into microwaves, but it's still the same light that escaped the early universe. When scientists measure the CMB, they're catching photons that have been traveling since the dawn of time, photons that have crossed the entire observable universe, just to land in a detector and say, this is what it was like back then. It's humbling, really. Every time you look up at the night sky, you're not just seeing objects scattered through space. You're seeing time itself, layered and stacked Like pages in a history book. The moon is about 1 second in the past. The sun is 8 minutes in the past. Alpha Centauri is 4 years in the past. Andromeda is 2.5 million years in the past. And the farthest galaxies we can see are over 13 billion years in the past. The night sky isn't a snapshot of the universe as it is. It's an archive of the universe as it was delivered to us one photon at a time, moving at the only speed light knows how to move. And all of this is possible because of that speed limit, because light can't go infinitely fast, because it takes time, real measurable time, for information to cross the void. That delay, that lag between event and observation, is what opens the door to the past. It's what lets us be witnesses to cosmic history. So the next time you find yourself under a dark sky, gazing up at the stars, remember this: you're not just looking out into space, you're looking back in time. You're seeing light that left its source years, centuries, millennia, even eons ago. You're standing at the end of a very long journey, and every photon that reaches you is a traveler with a story to tell. The universe, in its quiet way, is sharing its history with you, and the speed of light, that constant, unwavering 300,000 kilometers per second, is the storyteller carrying those stories across the void, one beam at a time, until they finally arrive at your eyes and whisper, "This is how it was. This is where we've been." And maybe that's one of the most beautiful things the speed of light does. It doesn't just connect us to distant places, it connects us to distant times. It turns the night sky into a living museum, a gallery of the past, constantly updating as new light arrives from farther and farther away. Time and space woven together by light, and all of it moving at exactly the pace the universe allows. But if light's speed creates this window into the past, it also enforces something even more fundamental: the order of events. It protects causality itself. And that protection, that cosmic guardrail, is what keeps the universe from falling into paradox and chaos. We've seen how the speed of light creates boundaries in space-time, how it limits what can influence what, and how it turns the night sky into a window on the past. But there's something even more fundamental happening beneath all of this, something that might be the most important consequence of light's speed limit. It protects causality. Causality is the idea that causes come before effects, that if you drop a glass, it falls and shatters, not the other way around, that you send a message and then someone receives it, not before you've sent it. It's so basic, so deeply woven into our experience of reality that we rarely stop to think about it. Of course, causes come first. What else would make sense? But if the speed of light weren't a hard universal limit, if information could travel faster, then light causality itself would break down. And when causality breaks, the logical structure of the universe starts to unravel. Let's walk through this gently, because it's one of those ideas that sounds abstract until you see it up close. Imagine you have a device that can send messages faster than light. Let's say you're on Earth, and you send a message to a friend on a distant planet, and that message arrives instantly, or even faster than a beam of light could make the trip. Seems harmless, right? Just a really good communication system. But now imagine your friend who's moving relative to you at a high speed sends a message back. From their perspective, because of the way relativity warps time, for moving observers, their reply might arrive before you sent your original message, not just in their time frame, in yours. You'd receive an answer to a question you haven't asked yet. And if that's possible, then you could, in theory, send a message to your own past. You could tell yourself not to send the first message, but if you don't send it, you never get the reply, which means you never send the warning, which means you do send the original message, which means, and round you go tangled in a loop with no exit. This is what physicists call a causal paradox, and it's not just a fun puzzle for science fiction writers. It's a genuine, logical impossibility, the kind of thing that would break the coherent structure of reality. The universe doesn't allow this, and the way it prevents it is beautifully simple. Nothing can go faster than light. No particle, no signal, no information. The speed limit isn't just about speed. It's about preserving the order of events, ensuring that causes always precede their effects, no matter who's observing or how fast they're moving. Think of it like this. The speed of light is a cosmic guardrail. It keeps the timeline from folding back on itself. It ensures that you can't accidentally become your own grandfather, that you can't receive an email before it's sent, that you can't step on a butterfly in the past and erase your own existence. Those kinds of paradoxes are fascinating to think about, but they're also nightmares for logic. And the universe, for all its strangeness, remains relentlessly logical. The speed of light says you may travel forward in time at whatever rate your speed dictates, but you cannot travel backward. You cannot undo. You cannot warn your past self. The arrow of time points one way, and I'm here to make sure it stays that way. Now, let's bring this down to something tangible, something you interact with, even if you don't realize it. When you make a phone call to someone across the world, there's a tiny delay measured in fractions of a second as the signal travels through fiber optic cables or bounces off satellites. You probably don't notice it in casual conversation, but it's there. That delay is the speed of light enforcing causality. Your words leave your mouth travel as electromagnetic waves and arrive at the other person's ear a moment later. Cause then effect, always in that order. When NASA sends a command to a rover on Mars, the engineers have to wait, sometimes 4 minutes, sometimes 20, depending on the planet's positions. If the rover is about to drive off a cliff, there's nothing they can do in real time. The light carrying their stop command hasn't reached Mars yet. By the time it does, the rover will have already made its decision. The delay isn't a technical limitation, it's a fundamental feature of the universe. Information cannot travel faster than light, and so causality is preserved even across interplanetary distances. You might think of this as frustrating. Why can't we just communicate instantly? Why do we have to wait for light to carry our messages across space? But here's the thing, that delay is what keeps everything sane. It's what prevents paradoxes. It's what ensures that the universe has a consistent timeline, that events unfold in a coherent sequence, that you can trust your memories because the past is actually genuinely past and not some fluid, changeable thing that could be rewritten at any moment. The speed of light doesn't just limit how fast we can go, It limits how much chaos is possible. It draws a line and says, beyond this logic breaks. So we stop here. And there's something oddly comforting about that, isn't there? In a universe that can seem vast and strange and full of mysteries, there's a rule that holds steady. A rule that says time flows forward, that causes lead to effects, that the story of the universe has a beginning, a middle, and a direction. Not because someone decided it should be that way, but because the structure of space-time, the relationship between light space and time, makes it inevitable. So the next time you're waiting for a web page to load, or for a message to send, or for a video call to catch up, after a moment of lag, remember, you're not just waiting for technology to do its job. You're waiting for light to carry information at the only speed it's allowed to travel. And in that waiting, you're experiencing one of the universe's most fundamental rules. Causality is protected, the timeline is secure, and paradoxes, for all their appeal in fiction, remain safely in the realm of impossibility. The speed of light isn't an inconvenience. It's the foundation of a universe that makes sense. But causality isn't just an abstract concept. It affects the technology we use every day, from the GPS that guides you to the nearest coffee shop to the very definition of what a meter means. Let's see how this cosmic speed limit has become woven into the fabric of modern life. So far, we've been drifting through some fairly abstract ideas: light cones and causality, time dilation, and the structure of space-time. These are big cosmic concepts, the kind of things that feel distant and theoretical, like they belong in textbooks rather than in your everyday life. But here's the beautiful secret: the speed of light and all the strange consequences that come with it aren't just out there in distant galaxies or high-speed particle accelerators. They're in your pocket, they're in your car, they're guiding you to the grocery store and helping you figure out what time your friend's flight is supposed to land. The speed of light and Einstein's theories about how it warps time and space are working right now quietly, invisibly, to make your life a little easier. And one of the clearest, most everyday examples of this is the Global Positioning System, GPS. Let's talk about how it works, because it's genuinely remarkable. When you open a map app on your phone and ask it to find the nearest bakery, your device connects to a network of satellites orbiting Earth. There are about 30 of them up there, moving at around 14,000 kilometers per hour, circling the planet twice a day. Each satellite carries an extremely precise atomic clock, and each one constantly broadcasts a signal that includes the exact time the signal was sent. Your phone picks up signals from at least 4 of these satellites. By comparing the timestamps on those signals with the time they arrive at your phone, your device can calculate how far away each satellite is. And once it knows the distance to 4 satellites, it can triangulate your position on Earth's surface with impressive accuracy, often to within a few meters. Sounds simple enough, right? Measure the time it takes for signals to travel, calculate distances, figure out where you are. But here's the catch: for this system to work, the timing has to be incredibly precise. We're talking about nanoseconds, billionths of a second. If the clocks on those satellites are off by even a tiny amount, your GPS will think you're in the wrong place. A timing error of just 1 microsecond translates to a position error of about 300 meters. That's the difference between your phone telling you you're at the bakery and telling you you're 3 blocks away in someone's backyard. So, the clocks have to be perfect. And this is where relativity comes in. Those satellites are moving fast, really fast, relative to someone standing on Earth's surface. And according to Einstein's special relativity, when you move fast, time slows down for you. To an outside observer, the clocks on those satellites should be ticking slightly slower than clocks on the ground. This effect is called time dilation, and we've talked about it before. It's real, it's measurable, and it matters. But there's another twist. Those satellites are also much higher up than we are, farther from Earth's center, where the pull of gravity is weaker. And according to Einstein's general relativity, time moves faster in weaker gravitational fields. So, from that perspective, the clocks on the satellites should be ticking slightly faster than clocks on the ground. Two effects pulling in opposite directions. Time dilation from speed says the satellite clocks run slow. Gravitational time dilation says they run fast. So, which one wins? It turns out the gravitational effect is stronger. The net result is that clocks on GPS satellites tick about 38 microseconds faster per day than clocks on Earth. That might not sound like much, but remember, a single microsecond of error means 300 meters of position error. If we didn't correct for relativity, GPS would accumulate errors of about 10 kilometers per day. Within a week, your phone would think you're in a completely different city. So, engineers programmed the satellite clocks to tick slightly slower than they should, compensating for both relativistic effects before the satellites even leave the ground. Once they're in orbit, their clocks sync up perfectly with clocks on Earth, and the system works beautifully. Every time you check your location, every time you get turn-by-turn directions, every time your food delivery app tells you the driver is 2 minutes away, you're relying on Einstein's equations. You're benefiting from our understanding of how the speed of light shapes time and space. It's not just a theory. It's not just something physicists talk about in universities. It's in your hand, guiding you through the world, accurate to within a few steps. And it's not just GPS. The speed of light underpins so much of the technology we take for granted. Your internet connection, whether it's fiber optic cables or wireless signals, data is traveling as pulses of light or electromagnetic waves moving at or near the speed of light. Every time you stream a video, send an email, or load a website, information is racing through cables and air at 300,000 kilometers per second, or a bit slower, in materials bouncing through routers and servers, and eventually arriving at your device, your phone's screen. It emits light photons generated by tiny LEDs or liquid crystals that travel to your eyes and let you see images, text, colors. The entire visual interface you interact with is light, carefully controlled and directed. Even the simple act of seeing is governed by light's properties. When you look at this text, photons are bouncing off the screen or the page if you're reading on paper, traveling through the air, passing through the lens of your eye, and landing on your retina, where they trigger chemical reactions that your brain interprets as vision. Light is the messenger between the world and your perception of it, medical imaging, X-rays, MRIs, CT scans, all rely on understanding how different forms of electromagnetic radiation interact with the body. X-rays are just high-energy photons that pass through soft tissue but get absorbed by denser material like bone, creating those ghostly images doctors use to see inside you without cutting you open. Microwaves in your kitchen, they're just low-frequency electromagnetic waves, part of the same spectrum as visible light tuned to make water molecules vibrate and heat up your leftovers. Radio, television, Wi-Fi, Bluetooth, all of these are light just at frequencies your eyes can't detect. They're all traveling at the speed of light, carrying information encoded in their wavelengths and frequencies. So when we talk about the speed of light having a limit, when we talk about relativity bending time and space, we're not talking about abstract distant things. We're talking about the foundation of the modern world, the technology that connects us, guides us, entertains us, heals us. It all rests on our understanding of light and how it moves through the universe. And it all works because the speed of light is constant, because it's the same for everyone, because it's woven into the structure of reality in a way that's predictable, reliable, and with the right equations, perfectly understandable. The universe may be strange, but it's also consistent. And that consistency is what lets us build tools that work, technologies that function, systems that guide us safely from one place to another. The next time your GPS tells you to turn left, take a moment to appreciate what's really happening. You're not just using a gadget, you're harnessing the fundamental geometry of space-time. You're benefiting from a cosmic speed limit that shapes reality itself. And honestly, that's pretty extraordinary. So light's speed shapes technology, protects causality, and opens windows to the past. But what about the people who wondered if we could break the rules? What happens when we try to go faster, or find loopholes, or imagine ways around the cosmic speed limit? That's where our journey takes its next turn, into the realm of the impossible, the hypothetical, and the beautifully stubborn boundaries of what the universe allows. By now you've probably noticed a theme running through everything we've talked about. The speed of light is constant. It's the same for everyone. It creates boundaries, protects causality, shapes time and space. It's fundamental, universal, unchanging. And yet, human beings have a particular habit when faced with limits. We immediately start wondering how to get around them. We've broken the sound barrier. We've split the atom. We've sent robots to other planets and built machines that can see inside the human body without cutting it open. So it's natural to ask, could we break the light barrier too? Could we find some clever trick, some loophole in the laws of physics that would let us go faster than light? It's a tempting thought. After all, the universe is vast. The nearest star is over 4 light years away. The nearest large galaxy is 2.5 million light years away. If we're limited to slower than light travel, the cosmos feels frustratingly out of reach. We could send a spacecraft to Alpha Centauri, but it would take tens of thousands of years with our current technology. Whole civilizations would rise and fall before it arrived. So physicists, especially the more imaginative ones, have spent a lot of time thinking about whether there might be a way around the limit, not to break the rules exactly, but to bend them, to find a creative solution that respects the laws of physics while still getting us where we want to go. And they've come up with some fascinating ideas. Let's start with one that sounds almost too good to be true: the warp drive. The concept is simple, at least in principle. Instead of moving your spacecraft through space faster than light, what if you could warp space itself? What if you could contract space in front of your ship and expand it behind you, creating a bubble that carries you along, like a surfer on a wave? Technically, you wouldn't be moving through space faster than light. Space itself would be moving, and you'd just be sitting inside a bubble, coasting along. The light speed limit would remain intact. Nothing inside your local bubble of space-time would be moving faster than light relative to the space around it. But from the perspective of someone watching from far away, you'd appear to cross distances faster than a beam of light could. This isn't pure fantasy. In 1994, a physicist named Miguel Alcubierre wrote down equations showing that mathematically, at least this kind of space-time warping is allowed by Einstein's general relativity. The math works. On paper, a warp drive is possible. But, and this is a significant, but it comes with some rather challenging requirements. First, you'd need something called exotic matter, a hypothetical substance with negative energy density. We've never seen exotic matter. We don't know how to make it. We're not even sure it can exist. It's a bit like saying, sure, you can build a flying castle as long as you have anti-gravity bricks. Technically possible, maybe, but not exactly practical. Second, even if exotic matter exists, the energy requirements for a warp drive are astronomical. Some estimates suggest you'd need the energy equivalent of the mass of Jupiter just to move a small spacecraft. That's not a fuel tank you can fill at the corner station. So, while warp drives are mathematically possible, they remain firmly in the realm of interesting ideas we can't actually build. Then there are wormholes, tunnels through space-time, that could, in theory, connect two distant points almost instantly. Imagine folding a piece of paper so two dots on opposite sides touch. The wormhole is the shortcut through the fold, bypassing the long journey across the surface. Again, the math allows for this. Einstein's equations don't forbid it. But the practical problems are enormous. Wormholes, if they exist, would likely be incredibly unstable, collapsing almost as soon as they form. Keeping one open would require, you guessed it, exotic matter with negative energy. And even if you could stabilize a wormhole, there's the uncomfortable possibility that traveling through one could create time travel paradoxes, loops, where cause and effect get tangled up in ways that break causality. The universe, it seems, has a way of closing every loophole we think we've found. What about quantum entanglement? Two particles linked in such a way that measuring one instantly affects the other, no matter how far apart they are. Einstein called it spooky action at a distance. And it genuinely seems to happen faster than light. But here's the key detail. While the correlation between entangled particles is instantaneous, you can't use it to send information. You can't control what result you'll get when you measure your particle, so you can't encode a message. It's like having two magic coins that always land on the same side when flipped, no matter how far apart they are. Spooky, yes. Useful for communication, no. The universe allows the correlation, but it carefully prevents us from using it to violate causality. Once again, the speed of light stands firm as the ultimate limit for transmitting information. There's also Cherenkov radiation, a phenomenon where particles moving through a material can briefly go faster than light moves in that same material. When light travels through water, for instance, it slows down due to interactions with the water molecules. A charged particle, under the right circumstances, can move through the water faster than that reduced light speed, creating a blue glow, a kind of optical sonic boom. But this doesn't break the universal speed limit. Light in a vacuum is still the ultimate cap. Cherenkov radiation is just a quirk of how light behaves in materials. Every time we think we've found a way around the limit, the universe gently but firmly closes the door. The speed of light remains unbroken, unbeaten, inviolate. And maybe that's okay. Maybe the limit isn't a frustration. Maybe it's a gift. Because that limit is what gives the universe structure. It's what keeps time flowing in one direction. It's what prevents paradoxes and preserves causality. It's what makes the cosmos understandable, predictable, safe. Without the speed limit, the universe could be chaos, a place where effects precede causes, where the past is mutable, where the rules change depending on who's asking. Instead, we have a universe with order, with logic, with a timeline that makes sense. The speed of light doesn't trap us. It grounds us. It gives us a foundation to build on a constant. We can trust a rule that holds steady even when everything else seems strange. And honestly, for something that lets us see the stars, understand the cosmos, and navigate the world with GPS, that's more than enough. The universe has a speed limit, and maybe we don't need to go any faster. We've explored the speed limit, watched it bend reality, and seen how it protects the order of things. But knowing the rules is only half the story. The other half, the part that might matter most, is understanding what light actually does with that speed, how it connects everything, how it carries the universe's story from the beginning of time right into your eyes, right now, tonight. Take a moment, if you will, to imagine a single beam of light drifting through the vast emptiness of space. No planets, no stars, no gravity pulling at it. Just one solitary photon gliding effortlessly through the vacuum, neither speeding up nor slowing down. It has no mass, no rest, and no need for fuel. It simply exists in motion, moving at the only speed it knows, 299,792,458 meters per second. That image, simple and serene, is more than just a poetic thought. It's a glimpse into the very fabric of the universe, because that humble little beam of light is doing more than traveling. It's participating in the great cosmic symphony, a dance of information, energy, and time that weaves the structure of everything we know. Let's begin with one of the most awe-inspiring pieces of light's legacy, the cosmic microwave background, or CMB. This isn't just a fancy name. It's the oldest light in the universe. It's been traveling unbothered and undisturbed for nearly 14 billion years. This faint uniform glow fills the entire universe and gently bathes everything in its presence. It's not the light from stars or galaxies. It's something far more ancient, the cooled down remnant of the very moment the universe became transparent. Here's what happened. About 380,000 years after the Big Bang, the universe had finally cooled enough for atoms to form. Before that moment, the cosmos was like a dense fog, opaque, chaotic, impossibly hot. Electrons and photons were locked in constant interaction, scattering off each other endlessly. Light couldn't travel freely. It was trapped, bouncing around in a sea of charged particles. But once the temperature dropped, enough electrons combined with protons to form neutral hydrogen atoms. Suddenly, photons had room to move. They could finally travel without constant interference. And so they did. They set off in all directions, a sea of ancient radiation carrying the imprint of the early universe. That light is still here. It's everywhere. It surrounds you right now, invisible to your eyes, because it's been stretched by the expansion of space, redshifted from visible light down into microwaves. But it's the same light that escaped the early universe, and it's still traveling, still carrying its ancient message. When scientists measure the CMB, they're literally catching photons that have been traveling since the dawn of time. These particles of light have never rested. They've crossed the universe just to gently land in a detector and whisper, "Here's what it was like back then." That's not just history, that's cosmic archaeology. It's like holding a 14 billion-year-old postcard in your hands. The CMB tells us the universe was once much hotter, much denser, and remarkably uniform. The tiny variations in its temperature, measured to a precision of a few millionths of a degree, reveal the seeds of everything that came after: galaxies, stars, planets, us. Those tiny ripples in the ancient light are the echoes of quantum fluctuations in the first fraction of a second after the Big Bang blown up to cosmic scales. Every structure in the universe today, from the smallest asteroid to the largest galaxy cluster, traces its origin back to those subtle patterns in the CMB. Light doesn't just show us the past, it shows us how the past became the present. And light does this because it has a speed. If it traveled infinitely fast, we'd only see the now. But because it takes time, real measurable time, to cross space, we get to look back. We get to see layers of history, each one older than the last, preserved in the patient journey of photons. But the story doesn't stop there, because light doesn't only tell us where we've been, it also powers nearly everything we experience right now. Let's talk about photosynthesis. It's easy to overlook, but photosynthesis is perhaps the most important chemical process on Earth. It's the engine behind almost all life, and it starts when sunlight, those same massless particles we've been talking about, hits a leaf. Here's what happens. Photons from the sun strike chlorophyll molecules inside plant cells. The energy from those photons excites electrons, kicking them into higher energy states. This triggers a cascade of chemical reactions that eventually store energy in the bonds of glucose molecules, sugar. The plant uses that stored energy to grow, to build roots and stems and leaves and seeds. And then animals eat the plants, or they eat the animals that eat the plants. Energy flows up the food chain, passed from organism to organism, all the way to you. Every meal you've ever eaten, every calorie that's powered your body, traces its origin back to photons from the sun, absorbed by plants through photosynthesis. In a very real sense, you are made of sunlight, not metaphorically, literally. The energy in your cells, the fuel that keeps you warm and moving and thinking, came from light. Photons traveled 150 million kilometers from the sun, landed on a leaf, got converted into chemical energy, and eventually found their way into you. Without light, there is no photosynthesis. Without photosynthesis, there are no plants. Without plants, the entire structure of life on Earth collapses. The food chain breaks. The oxygen we breathe, also a byproduct of photosynthesis, disappears. Light doesn't just let us see the world, it builds the world. It's the invisible hand that turns carbon dioxide and water into living matter using nothing but the energy carried by photons. And it's not just plants. Your own body is deeply tuned to light. Your circadian rhythm, your internal clock, is regulated by exposure to sunlight. When morning light enters your eyes, it signals your brain to stop producing melatonin, the hormone that makes you sleepy. You wake up, you become alert. As the day fades and light dims, melatonin levels rise again, nudging you gently toward rest. Even now, as you listen to this, your body is tracking the light around you, adjusting its rhythms, syncing itself to the world's natural cycles. You are in a quiet way, a creature of light, shaped by it, guided by it, fed by it. Light is the thread that connects the ancient cosmos to your dinner plate, the Big Bang to your breakfast. It carries energy across space, delivers it to Earth, powers the chemistry of life, and regulates the rhythm of your days. And all of it moves at 300,000 kilometers per second, fast enough to cross the void, but slow enough to take time to carry history, to let us see where we've been and understand how we got here. So, when you see a plant growing in the sunlight, or feel the warmth of the sun on your skin, or notice how a bright morning makes you feel more awake, remember, you're witnessing light doing what it's always done, traveling, connecting, giving, never resting, never stopping, always moving at the only speed it knows. The oldest light in the universe is still out there, drifting through space, carrying the story of the beginning. And the newest light photons, born in the sun just 8 minutes ago, is landing on leaves and skin and solar panels, right now, powering the present moment. Light is the bridge between then and now, between there and here, between the cosmos and your eyes. But light doesn't just connect us to the past or fuel the present. It also binds us to each other, carries our voices across distances, and paints the world in color and meaning. Let's see how light becomes the language through which we understand everything. Light is more than just a traveler or a messenger. It's a language. The universe speaks to us in photons, and we've learned slowly and painstakingly over centuries how to listen. Every time we see something, we're not just passively receiving an image, we're interpreting a message encoded in wavelengths, intensities, and patterns. Light carries information about distance, temperature, composition, motion, and our eyes, our instruments, even our technology are designed to decode it. Let's start with the simplest, most immediate way. Light communicates color. When you look at a ripe strawberry and see red, what's really happening? The strawberry isn't generating light. It's not glowing. What's happening is that sunlight, which contains all the colors mixed together, hits the strawberry's surface. The molecules in the strawberry skin absorb most of those wavelengths, but they reflect back the ones that correspond to red light. Those reflected photons travel to your eyes, where they're captured by specialized cells called cones. You have 3 types of cones, each sensitive to different ranges of wavelengths, red, green, and blue. The combination of signals from these 3 types of cones is what your brain interprets as color. The strawberry sends red light. Your cones catch it. Your brain translates it, and you perceive red. But here's the beautiful, slightly unsettling part. Color doesn't exist out there in any absolute sense. It's a conversation between light matter and mind. The strawberry reflects certain wavelengths. Your eyes detect them. Your brain gives them meaning. Somewhere in that dance, the experience of redness emerges. Different creatures see color differently because they have different types of photoreceptors. Some birds can see ultraviolet light wavelengths invisible to us. Some animals see only in black and white. The universe sends the same photons to all of us, but we each translate them differently. Color is relational, contextual, a product of biology meeting physics. And it's not just color. Light also carries information about how far away something is and how fast it's moving. When astronomers look at distant galaxies, they notice something curious. The light from those galaxies is shifted toward the red end of the spectrum. This red shift happens because the galaxies are moving away from us, or more precisely, because the space between us and them is expanding. As space stretches, it stretches the light traveling through it, increasing its wavelength, shifting it toward red. The farther away a galaxy is, the faster it's receding, and the greater the redshift. By measuring how much the light has been shifted, astronomers can calculate both the distance to the galaxy and the speed at which it's moving. Light doesn't just show us where things are, it shows us how the universe is changing. Light also tells us what things are made of. When you pass light through a prism, it splits into a rainbow of colors. But if you look closely at the light from a star and spread it out into a spectrum, you'll see something more thin, dark lines scattered throughout the rainbow. These are called absorption lines, and they're caused by atoms in the star's atmosphere, absorbing specific wavelengths of light. Each element has its own unique pattern of absorption lines, like a fingerprint. Hydrogen absorbs certain wavelengths. Helium absorbs others. Sodium, calcium, iron, each leaves its mark on the light passing through. By studying these patterns, astronomers can tell what a star is made of, even if that star is millions of light years away. They can measure its temperature, its age, its motion. They can even detect planets orbiting distant stars by watching for tiny dips in starlight as the planet passes in front of its host star. All of this information, distance, speed, composition, temperature, is carried by light, encoded in its wavelength, its intensity, its spectrum, and we've learned to read it. This is why light is often called the universe's messenger. It doesn't just illuminate, it informs. Every photon carries a story about where it came from, what it passed through, how long it's been traveling. But light doesn't just connect us to distant stars, it connects us to each other. Every form of communication you use, text messages, phone calls, video chats, emails, relies on light or its electromagnetic cousins. When you send a text, the signal is transmitted as electromagnetic waves, moving at the speed of light through the air or through fiber optic cables. When you make a video call, your image is broken down into digital information, converted into pulses of light, sent across continents through undersea cables, and reassembled on someone else's screen. Light is the medium through which we stay connected. It carries our words, our faces, our voices across distances that would have seemed impossible just a century ago. And even when you're sitting across from someone having a conversation in person, light is still the messenger. You see their face because photons bounce off their skin and into your eyes. You read their expression, notice their smile, see the way their eyes crinkle. When they laugh, all of it delivered to you by light. In a sense, every interaction you have with the world is mediated by light. You can't touch a distant star, but you can see it because its light reaches you. You can't physically be in two places at once, but you can see someone on the other side of the world because light carries their image to you. Light is the thread that weaves the universe together. It connects the distant past to the present moment. It links atoms to galaxies, stars to eyes one person to another. And it does all of this while obeying that one simple, unbreakable rule. It moves at 300,000 kilometers per second. No faster, no slower. Always the same for everyone everywhere. There's something profound in that constancy. In a universe that can seem chaotic and unpredictable, light is reliable. It follows the same rules today that it followed 14 billion years ago. It travels the same speed on Earth as it does in the most distant galaxy. It's a constant. We can trust, a foundation we can build on. And maybe that's the deepest truth about light. It's not just what lets us see. It's what lets us know. It's the language the universe uses to tell its story. And we curious, persistent, stubborn creatures that we are, have learned to listen. We've learned to catch ancient photons from the edge of the observable universe and read the history written in their journey. We've learned to split light into spectra and decode the chemical fingerprints of distant stars. We've learned to send our own messages riding on beams of light, connecting people and places that would otherwise be impossibly far apart. Light is the universe's gift to us, a way to see, to know, to connect, to understand. And it's been traveling patiently since the beginning of time, just waiting for someone to notice, just waiting for eyes to evolve, for minds to wonder, for hands to build telescopes and cameras and fiber optic cables. The universe has been speaking to us in light all along. We're only just learning to speak back. And now, as we drift toward the end of this journey, there's one more thing to understand. Light doesn't just connect us to the universe. It connects us to ourselves, to the atoms in our bodies, the energy in our cells, the very substance of who we are. There's a phrase you might have heard before, usually delivered with a sense of wonder. We are made of stardust. It sounds poetic, almost mystical, the kind of thing someone might say while gazing up at the night sky with a faraway look in their eyes. But it's not just poetry. It's literally precisely scientifically true. And light is the reason why. Let's trace this story back to the beginning, slowly, gently, the way you might follow a thread through a tapestry. In the very early universe, just after the Big Bang, there were only the simplest elements, hydrogen and helium, with tiny traces of lithium. That's it. No carbon, no oxygen, no iron, no calcium. None of the elements that make up your body, the earth, or anything complex existed yet. The universe was chemically simple, almost boring. But then, over millions of years, gravity pulled those clouds of hydrogen and helium together. They collapsed under their own weight, heating up as they compressed, until finally the cores became hot and dense enough for nuclear fusion to begin. Stars were born. Inside those stars, hydrogen atoms fused together to form helium. Helium fused to form carbon and oxygen. In the hottest, most massive stars, the fusion continued. Carbon and oxygen combined to make neon magnesium silicon. Silicon fused to create iron. Each step released tremendous amounts of energy, the light and heat that make stars shine. And here's the crucial part: that light, that energy radiating out from the star, is what prevented the star from collapsing under its own gravity. Fusion creates light. Light creates pressure. Pressure holds the star up. It's a delicate balance, a cosmic dance between gravity, trying to crush the star, and light pushing outward to keep it stable. For millions, sometimes billions of years, this balance holds. The star shines steadily, fusing lighter elements into heavier ones layer by layer, like an onion made of different elements. Hydrogen burning in the outer layers, helium deeper in, carbon, oxygen, silicon, all the way down to an iron core at the center. But iron is where the process stops. Fusing iron doesn't release energy, it consumes it. So, once a massive star builds up an iron core, it's in trouble. There's no more fuel, no more outward pressure from fusion, and gravity, patient and relentless, finally wins. The core collapses in a fraction of a second. The outer layers crash inward, rebound off the collapsing core, and explode outward in one of the most violent events in the universe, a supernova. In that explosion, temperatures and pressures become so extreme that even heavier elements are forged: gold, silver, platinum, uranium. Elements that can't be made inside a normal star are created in those final cataclysmic moments. And all of it, the carbon, the oxygen, the iron, the gold, all the elements heavier than hydrogen and helium, gets blasted out into space at tremendous speeds. Those expanding clouds of enriched gas drift through the galaxy. They mix with other gas clouds. They collapse again under gravity, and new stars form, this time surrounded by disks of material that contain not just hydrogen and helium, but all those heavier elements forged in previous generations of stars. Planets form from those disks, rocky planets like Earth, made of silicon and iron and oxygen, and eventually, on at least one of those planets, life emerges. Life that builds its molecules out of carbon and oxygen and nitrogen and phosphorus elements that didn't exist in the early universe, elements that had to be made inside stars and scattered by supernovae. The calcium in your bones was made in a star. The iron in your blood was forged in a supernova. The oxygen you're breathing right now was created by fusion deep inside an ancient sun that exploded long before our solar system even existed. You are quite literally made of atoms that were assembled inside stars and delivered across the galaxy by starlight and supernova explosions. But there's another layer to this story, one that ties back to light in an even more direct way. The energy that powers your body, the energy that lets you move, think, breathe, comes from the food you eat. And that food, whether it's a plant or an animal that ate plants, ultimately gets its energy from photosynthesis, from sunlight absorbed by chlorophyll and converted into chemical bonds. So not only are your atoms made from stars, but the energy animating those atoms right now came from the sun, came from light. Photons that traveled 150 million kilometers struck a leaf and got trapped in molecules of sugar that eventually found their way into you. You are stardust, yes, but you're also animated by starlight, powered by it, shaped by it. Every breath you take, every thought you think, every step you walk, it's all running on solar energy captured by plants and passed along to you. You're a walking, talking collection of ancient atoms held together by the energy of photons. And there's something deeply humbling about that, isn't there? You're not separate from the universe, not an observer standing outside looking in. You're part of it, made from it, connected to it at the most fundamental level. The atoms in your left hand might have come from a different star than the atoms in your right hand. The iron in your blood might have been scattered by a supernova billions of years ago, drifted through space, eventually accreted into the disk of gas and dust that became our solar system, incorporated into the forming Earth, cycled through the planet's geology, for eons taken up by plants eaten by animals, and finally ended up in you. That's not a metaphor. That's your history. That's where you came from. And light was the messenger. At every step, light from the first stars illuminated the early universe. Light from dying stars carried the elements into space. Light from our sun powers the chemistry that keeps you alive. Light from distant galaxies reaches your eyes and reminds you that you're part of something vast and ancient and ongoing. You're not just looking at the universe, you're made of it. And light is the thread that connects you to all of it, to the Big Bang, to the first stars, to distant galaxies, to the sun, to the leaves outside your window, to the food on your plate. Every photon that touches you is part of that connection. A reminder that you belong to the cosmos, that you're woven into its fabric, that the boundary between you and the universe is far more blurred than it might seem. So the next time you feel the warmth of sunlight on your skin, take a moment to appreciate what's really happening. You're not just feeling heat, you're feeling the energy of nuclear fusion carried across space by photons delivered to you after an 8-minute journey from the sun's core. You're feeling the same process that powers stars, that forges elements, that makes the universe bright and warm and alive. You're feeling starlight because in a very real sense, you are starlight. Stardust animated by the energy of stars, seeing the universe through eyes, built from atoms made in stars, thinking thoughts, powered by photons from a star. It's enough to make you pause, isn't it? Enough to make you look up at the night sky with a different kind of wonder. Those aren't just distant points of light. They're your distant relatives, your ancestors in a sense. The forge is where your atoms were made, and the light from those stars traveling for years or centuries or millennia to reach your eyes is the family letter, the message from home, saying you came from here. You're part of this. Welcome home. But light doesn't just connect us to the distant cosmos. It also connects us to each moment, each experience, each fleeting instant of being alive. Let's bring the story back down to earth, back to now, back to the quiet miracle of seeing. We've talked about light traveling billions of years from distant galaxies. We've talked about ancient photons from the Big Bang and the way starlight forged the atoms in your body. But there's another miracle happening right now, so close and so constant that it's easy to forget how extraordinary it is. You can see. Think about that for a moment. You have 2 small organs in your skull, each about the size of a grape, that can capture light and turn it into experience, into color and shape and depth and motion, into faces and sunsets and words on a page, into the entire visible world. Vision feels effortless. You open your eyes, and there it is, the room, the sky, the tree outside the window. But what's actually happening is almost impossibly complex, a cascade of physics and chemistry and biology, all working together in perfect harmony. Let's slow it down and watch what happens when you see something, anything. Let's say you're looking at a tree. Light from the sun strikes the leaves of the tree. Some wavelengths get absorbed by the chlorophyll and other pigments in the leaves. But the wavelengths we associate with green bounce back reflected. Those photons travel through the air, billions of them, streaming away from the tree in all directions. A few of those photons happen to enter your eye. First, they pass through the cornea, the clear dome at the front of your eye. The cornea bends the light, starting the process of focusing. Then the light passes through the pupil, that black circle in the center, which is actually just an opening. The iris, the colored part of your eye, adjusts the size of the pupil, depending on how bright it is, letting in more light in the dark, less in bright conditions. Behind the pupil is the lens, a flexible structure that fine-tunes the focus, bending the light even more so that it converges at exactly the right spot at the back of your eye. And there at the back of the eye is the retina, a thin layer of tissue packed with specialized cells called photoreceptors. These are the cells that actually detect light. You have two types rods, which are sensitive to dim light and help you see in the dark, and cones, which detect color and work best in bright light. When a photon strikes one of these cells, it triggers a chemical reaction. A molecule called retinol, bound to a protein called opsin, changes shape when hit by light. That shape change triggers a cascade of signals inside the cell, ultimately creating an electrical impulse that travels down the optic nerve to your brain. Each photoreceptor cell is doing this, constantly firing or not firing, depending on whether it's being hit by light. And you have about 120 million rods and 6 million cones in each eye, all sending signals simultaneously, creating an incredibly detailed map of the light pattern falling on your retina. But here's where it gets even more remarkable. Your brain doesn't just receive that map passively. It interprets it. It processes the signals, looks for edges and patterns, compares the input from your left and right eyes to create depth perception, tracks motion, adjusts for lighting conditions, fills in gaps, and somehow, in ways we still don't fully understand, creates the unified, coherent, three-dimensional experience you call seeing the tree. The tree itself doesn't enter your eye. Not even an image of the tree, really. What enters your eye is a pattern of photons, different wavelengths, hitting different spots on your retina. Your brain takes that pattern and constructs the experience of a tree. And it does this in real time, constantly updating about 10 times per second, seamlessly integrating information from both eyes, tracking motion, adjusting for changes in light, remembering what things looked like a moment ago, and comparing that to what they look like now. All of that from photons, from light. Vision is so reliable, so constant, that we forget what an astonishing achievement it is. You're taking particles with no mass, no substance, just pure energy, and using them to construct a detailed, navigable model of the world around you. And it's not just passive observation. Vision guides your actions. You reach for a cup because you see where it is. You smile at a friend because you see their face. You read these words because light bouncing off the screen or page is creating patterns on your retina that your brain has learned to decode as language. Every interaction you have with the physical world is mediated by light. You navigate your home in the dark by remembering where things are, but in the light, you see them directly. You recognize faces, read emotions, appreciate beauty, notice danger, all through light. And here's a tender thought. When you look at someone you love, the light reflecting off their face travels into your eyes and creates a cascade of signals in your brain. In a very literal sense, they're touching you with light. The photons that bounce off their skin and enter your eyes are carrying information, the curve of their smile, the warmth in their eyes, the way they tilt their head when they're thinking. You're seeing them, yes, but you're also being touched by the light that touched them. Every moment of visual experience is a kind of connection, a physical link made of photons traveling from object to eye, carrying shape and color and texture and turning it into meaning. And all of it happens at the speed of light. The moment the photons enter your eye, the signals begin. Within milliseconds, your brain is processing them. Within a fraction of a second, you're aware of what you're seeing. Light doesn't just show you the world, it connects you to it instantly, continuously, seamlessly. There's also something poignant about how fragile and precious this connection is. If the light is too dim, you can't see. If it's too bright, you're overwhelmed. If the wavelengths are outside the narrow band, your eyes can detect infrared, ultraviolet, radio waves. They pass right through you, invisible as if they don't exist. You're only seeing a tiny slice of the electromagnetic spectrum, a narrow window that evolution happened to tune your eyes to because it's where the sun emits most of its light and where Earth's atmosphere is most transparent. There's an entire universe of light all around you that you'll never see with your eyes alone. But the slice you can see, that narrow band from red to violet, is enough. Enough to navigate the world, enough to recognize faces, enough to read and create and appreciate beauty, enough to watch the stars come out at night and wonder about your place in the cosmos. Vision is a gift, a partnership between physics and biology, between the universe sending light and your body capturing it, between photons and neurons, between the world and your awareness of it. And it's happening right now. Every moment you're awake, photons are streaming into your eyes, getting converted into signals, getting interpreted as experience, giving you this continuous, living, breathing sense of being present in a visible world. So, maybe just for a moment, appreciate what you're doing right now. You're seeing. You're taking light, massless, invisible energy and turning it into trees and faces and words and stars. You're catching the universe's messages written in photons and reading them in real time. That's not just remarkable, it's quietly miraculous. And now, as our journey together draws gently to a close, let's bring everything back to where we started, to the simple, profound question of why light has a speed limit and what that limit means for everything we've explored. And so, here we are, gently floating back to where we began. We set out tonight to answer a simple question: why does light have a speed limit? Along the way, we've wandered through fields of photons and danced with electromagnetic waves. We've listened to the whispers of the cosmic microwave background. We've watched time bend and space stretch. We've seen clocks slow down and stars speak in ancient beams. We've traveled through cables and galaxies, through your phone, your eyes, and the quiet glow of the oldest light in the universe. And the answer in the end is as elegant as it is profound. Light moves the way it does because the universe is built to let it and to be shaped by it. Its speed isn't just fast, it's fundamental, a cosmic rule that holds everything together from the pulse of atoms to the stretch of galaxies. It's not something that can be broken or outpaced, and perhaps that's a good thing. The speed of light gives us order. It gives us time. It gives us a way to understand. It gives us stories and sunsets and the warmth of starlight on a cold night. So maybe we don't need it to be faster. Maybe it's already perfect just the way it is. Think about everything that speed limit makes possible. It protects causality, ensuring that causes come before effects, that the universe has a logical timeline, that you can trust your memories because the past is truly past. It creates the light cone, drawing boundaries around what can influence what, giving structure to space-time, making the cosmos navigable and comprehensible. It opens windows to the past, letting us see distant galaxies, not as they are, but as they were, turning every telescope into a time machine, every photon into a messenger from history. It powers GPS satellites that guide you through your day, adjusting for relativity so precisely that without Einstein's equations, you'd be lost within hours. It enables all the technology you use: fiber optic cables, wireless signals, screens and cameras, and medical imaging, all built on our understanding of how light moves. It drives photosynthesis, capturing solar energy and turning it into food, into life, into the very fuel that powers your thoughts and movements. It forged the elements in stars and scattered them across space, building the atoms that would eventually become planets and people. It carries information across the universe, encoding temperature and composition and motion in wavelengths and spectra, teaching us what distant stars are made of and how the cosmos is changing. It creates vision, entering your eyes and becoming experience, turning photons into colors and shapes and faces and beauty. And it connects everything, past to present, stars to eyes, one person to another, the Big Bang to this moment right now as you listen and drift and wonder. All of that because light has a speed, because it moves at exactly 299,792,458 meters per second. Not faster, not slower, always the same for everyone, everywhere, forever. That's not a limitation. That's a foundation, a constant in a changing universe, a rule you can build a cosmos on. And now, as we bring this quiet journey to a close, let me ask you one last time. Where in the world are you listening from tonight? And what time is it right now wherever you are? Are you curled up in bed with the stars outside your window, or sitting quietly on the other side of the world, with morning light just beginning to rise? Wherever you are, and whenever it is, thank you for spending this time with me, for drifting through the cosmos at the speed of thought, following photons across space and time, wondering about the universe and your place in it. If this journey brought you some peace, some wonder, some quiet sense of connection to the larger world, I'd be grateful if you left a gentle, like a soft, subscribe. It helps others find their way here to this calm corner where science meets sleep, where curiosity meets rest. And if this video kept you awake, well, at least you learned something beautiful while waiting for sleep to find you. Not such a bad trade, really. Until next time, rest well, dream gently, and may your dreams move at just the right speed. Not too fast, not too slow, but exactly the pace you need. Remember, even in darkness, even in stillness, light is always on its way. From stars billions of years old, from the sun just 8 minutes away, from the lamp beside your bed. It's moving, always moving, at the only speed the universe allows. The perfect speed, 300,000 kilometers per second, not because it chose to, but because it must. Because the universe, for all its mystery and vastness, has structure, has order, has beauty. And at the heart of that beauty is light, steady and constant, connecting moments and places and people across the cosmos, one photon at a time. Good night, sleep well, and thank you for traveling with me tonight at the speed of light through the quiet wonders of the universe. And now, as your breathing slows and your thoughts begin to soften, let yourself drift. Let go of the numbers, the equations, the distant galaxies. Let them all fade into the quiet dark. What remains is simple light moves. It always has. It always will. At exactly the speed it needs to be. And you made of stardust, powered by sunlight, seeing the world through photons. You're part of that story, not separate from it, woven into it. So close your eyes now. Let the weight of the day fall away. The universe is still out there, turning glowing, sending light across impossible distances. The stars are still burning. The ancient photons are still traveling. And tomorrow, the sun will rise again, 8 minutes after its light begins the journey to find you. But tonight, you can rest. You've traveled far enough. You've learned enough. You've wondered enough. The light will keep moving. The cosmos will keep turning. And you can simply be here, breathing softly, drifting gently, held by the same laws that hold the stars. Sleep well, traveler. The universe will still be here. When you wake, goodbye.